Mr. Adams.
What do you want to know?
Everything. And I mean everything.
Well?
If you love listening to this show, please consider giving a rating and a review on Amazon Alexa or wherever you listen. We want to continue bringing you this amazing content, and part of our ability to do that means that we need a big audience. Now, it may not seem like much, but rating and reviewing the show will help more people find us, just like how you found this show. Simply on any podcast platform, search for a show, scroll down to the bottom, and push 5 stars. It's that easy. Thanks for supporting the show. So today I'm joined by Villarreal, who is the CEO of Infinite Composites Technologies that develops and manufactures advanced composite pressure vessels and structures. So Matt, welcome to the show today.
Glad to be here. Thanks for having me.
12 years ago, I guess, you had helped build a natural gas powered formula style race car. Tell us a little bit about that and how that became kind of the genesis of what you're doing today.
Sure, yeah. It's a really interesting story. One of my roommates who was obsessed with Formula One racing found out that our university had a team on campus who was, the goal was to design, develop, build one of these Formula One style cars and take it to compete against teams from all over the world. Long story short, they didn't have a lot of money and the team was about to be shut down, so we joined to help them raise funds and get the team back going again. And one of the ways we did that was to convert one of the cars to run on compressed natural gas, which used a heavy metal tank. And so we did a 24-hour endurance race with it and realized that the tank was about 10% of the weight of the vehicle and didn't really hold a lot of fuel. And so we basically went out and started searching for alternatives, found out that there weren't a lot of good options, and saw an article that basically said linerless composite tanks were the holy grail of gas storage. And that's what basically inspired me to come up with a concept for the technology, and that's what started the company.
So really the interesting question would be, did you guys help win the race?
The 24-hour endurance race was more for publicity or to prove the natural gas technology would work. We completed the 24 hours, which is pretty amazing because these cars were only made to go about 15 miles in their entire life, and we took this thing 700 miles in 24 hours. In competition, we didn't win the race, but we did place in the top 5 on the cost category, which was our goal. So I would say it was a success, and we got the team started back up again, and they've been making progress ever since.
Well, that's a terrific story and a very exciting story, actually. So let's get into your core technologies. You mentioned that you guys focus on linerless all composite tanks. What exactly does that mean?
Yeah, so traditionally, the most advanced gas storage tanks in existence all use a metal or plastic liner on the inside. So this thing's basically like a metal or plastic tank, and then you apply the carbon fiber. And what the liner does is it keeps the gas from permeating out of the tank, and then the carbon fiber is the strength to hold the pressure. And so we developed some new materials technologies and manufacturing processes that allow us to eliminate the need for that metal or plastic liner, and leave behind only the all carbon fiber shell. So it's basically a simplified design because the interaction between the liner and the composite are a big challenge and a major failure point. It basically reduces the mass of the tank by about 40%, the cost by about 50%, and the lead time by about 80% compared to state-of-the-art tanks for spacecraft.
So can you go into just a little bit of depth around your IP in terms of, is this a manufacturing process? Is this a chemical process? How are you guys able to do this?
Yeah, so we've basically developed some custom resin systems that we reinforce with carbon fiber. So when you have a composite, you have a reinforcement, which is the fiber, and then you have the resin, which holds all the fibers together. And so we've invented some new materials based on nano-scaled additives that make the composite structure more impermeable to gases, and two, it increases the strength of the overall structure. So we don't need any separate structures in there to maintain the pressure. And so that's one of the major parts of the technology is our resins and our material science. But in order to make the whole system work, we had to develop some new processes for one, making the form that the carbon fibers wrapped around. So usually that's the metal liner in these other processes. So we created something that is rigid and strong, and we can basically remove it out of the tank afterwards to leave behind that carbon fiber shell. And then the third kind of component of the technology is the process for bonding the metallic interfaces, which are basically like where you plug in the gas line to the composite structure. Usually, because the materials have different thermal expansion when they're heated and cooled, it'll create a break in between there. And so we've created a process that makes a very robust bond between those two materials. And we've been able to take these tanks to higher pressures than have ever been seen by anyone else who's done composite tanks like this.
That's very interesting, and it actually speaks to this notion of innovation that oftentimes it's not just a facet, but you really need to create a full out system to support this. In terms of the additive and the resin, is there a certain kind of a longevity or lifespan before the additive starts to wear down?
Not that we've seen. One of the additives that we use is graphene nanoplatelets, which is basically a one-dimensional carbon structure. Very robust, very hard to break down. But we've simulated basically 20 years of useful life on one of our tanks, and it actually got stronger over those pressure cycles. We're not fully sure on why that is, but we've seen it multiple times where pressurizing and depressurizing the tank has actually increased the strength of the composite over time.
And one last question on the material science before we move on is, have you guys considered other kind of substrate that could have that same rigidity and structural integrity, but can potentially even reduce the weight as well as even the cost to manufacturers?
Yeah, so right now, some of our processes for making that form on the inside are very manual, but one of the things that we've recently been able to do is implement a 3D printing type of application so that we can basically have this fully automated, which reduces the labor by about half on the overall tank, and increases basically the quality of the substrate, such that there's not a lot of rework and literally no labor has to go into it. So, we can go, we get the machine running before we leave, and then when we come back in the morning, and all the pieces are there ready to go to start winding. And so usually this process would take a lot longer, and you'd have a lot of kind of improvements or kind of hands-on to get the quality that you want to wind on. But with this process, we basically eliminated that. And so it's only working on a small scale now, but we're planning to scale this up on some of the larger tanks.
That's good to hear. So when we talk about graphene and nanotechnology, and then of course we're talking about pushing the boundaries of physics in terms of pressures and variability of cold and hot, how do these things, these kind of extremes, become applicable in a context within space?
Yeah, so if you consider like a space launch vehicle, like the Saturn V, which sent astronauts to the moon, basically the most of the structure, over 60% of the mass of that vehicle, was made up of its tanks, and those tanks are storing liquid oxygen and liquid hydrogen. So those are both cryogenic fluids that have to be stored. And as you're flying and pushing those fluids out to propel the rocket, you're getting some really interesting thermal gradients. So like the top of the tank might be like negative 100 degrees Fahrenheit, and the bottom of the tank might be negative 421 degrees Fahrenheit because it's holding liquid hydrogen. And so being able to kind of distribute that thermal gradient across the tanks, and also being able to keep the liquid inside at a very cold temperature has a major effect. And so with metal tanks, the heat conducts right out of it, and you have to have secondary insulation. But with our composite material, it has a very low heat transfer, and so we don't actually have to have secondary insulation on the outside of it to maintain the cold temperature.
Yeah, I think this is really interesting because of the fact that in space, we're talking about some serious volatility and quick, differences. So being able to handle the thermal differences or the variances, that's huge. And of course, if you didn't do that, the downside is, of course, safety issues and as well as longevity and maintenance issues. So it's pretty significant, given the fact that the bulk of that type of a vehicle or device really is holding these types of precious gases, like oxygen, for instance.
Yeah.
How are you guys supporting small satellites, by the way?
Yeah, so we've done some development on some satellite constellations being built by some of the tech entrepreneurs who are out there building rockets and trying to build satellite constellations. We've done some initial work with those guys. Nothing's flying yet, but we did just secure initial contract with Europe's largest satellite manufacturer for a low Earth orbit constellation of about 300 satellites. And so that'll likely be our first big production order with a prime. But in addition to that, we're also developing some much smaller tanks that can be integrated into CubeSat platforms. So they'll be very small, and our intent with that is to be able to sell these on our website, so that these universities and college students who are building a lot of these very small satellites, they can have access to the most advanced technology in the world, just with the swipe of a credit card on our website. And so that's one of our missions, is to basically accelerate the adoption of linerless composite tanks throughout not only space, but through transportation as well.
That's a really interesting strategy, because it kind of reminds me of Arduino, do-it-yourself types of, kits. You're basically allowing for these components to become readily available to developers and hardware engineers in different applications. So that's very intriguing. Can you talk a little bit, again, just a little bit deeper in terms of the satellites? Because, again, I know you're alluding to, but perhaps maybe your NDA doesn't allow for you to say the companies outright, like Starlink and others that are in this space. Tell us about when those small satellites are up there and they are constantly having to recalibrate their position to maintain the right height, altitude, as well as the proximity for that creation of, let's call it, mesh network. So what exactly are the kinds of things that your containers are holding, and how central is it to the operation of these satellite networks?
Yeah, sure. So typically in satellites, where our tanks are being used in electric propulsion systems. So for one of the constellations we did some work on, it was holding 5,000 psi krypton gas, and that was being passed through a Hall effect thruster. And basically, it's kind of like vaporizing the gas and just throwing mass out of the back of the thruster. And that's what allows it to move into the proper orbit and kind of change its position. The satellite constellation we're working on now is going to be holding 5,000 psi xenon, which is used in the same case. So it's basically just a different fuel for a very similar electric propulsion thruster. And it's a Hall effect thruster that it's being used on. And so, yeah, I mean, it's basically the fuel tank, but the fuel's not being combusted. It's basically being heated up and thrown out as mass to move the satellite in space.
And just out of curiosity, what happens when those gases deplete? Then how do you then start to operate the satellite, or is there a refuel process?
Yeah, so previously none of these satellites have been able to be refueled. So when they run out of propellant, basically they're usually just space junk. But there's been some recent efforts to do satellite refueling, and I believe it was Northrop Grumman who successfully did an orbital refueling demonstration. And then there's also some great startup companies who are using this as their primary product to be a fueling depot in space for refueling satellites. And so usually they're just dead, but there's a big push and a lot of people working on being able to refuel these. And so we're talking to a lot of those people about using our tanks, but it'll take a little bit for that technology to be widespread, but we're on the cusp of it right now.
So, we're talking about space today, and it's a nascent market, but there's a lot of things heating up. And of course, we even have the new military branch, Space Force, as well. So can you kind of forecast out in terms of the future of where things are going, whether it's space tourism, whether it's commercial, whether it's NASA related? What can we anticipate, and why do you feel that you are a key component of the maturity of space?
Sure, yeah, and I mean the effort to commercialize low Earth orbit is already underway. You can see this with the Starlink satellites and some of these other constellations that are basically starting to form in low Earth orbit. So that's kind of the first step, is being able to commercialize low Earth orbit. But alongside that, NASA and the global space community, honestly, are pushing for the Artemis program and the Lunar Gateway program, which is essentially to the end is to set up a permanent base on the moon. And so they'll have an orbiting kind of space station similar to the ISS orbiting the moon, and that'll kind of be a waypoint for both tourists and for industries to basically go to on their way to the moon, so that it can reduce the cost and the challenges of going back and forth from the surface of the moon to back to Earth. I think the space tourism is going to drive a lot of public attention and get a lot more people excited about space. I think it will be an interesting industry, but where I really see the industry going is moving a lot of the industrial kind of industries or industrial applications, industrial processes off of Earth onto the moon and eventually Mars and other places. Because once you leave Earth, the resources are basically infinite. So and one of the reasons why we're in a great position is because in order to move around in space, you have to have pressurized or cryogenic fluids to do that. I mean, some vehicles can move with solar, but those aren't vehicles that will be transporting people. They can't support the people living on them, and you'll need pressurized gas tanks for basically every vehicle that's going to have a man on it. And then for all these lunar landers, rovers, and exploratory vehicles are going to have that onboard propulsion. And some of them may not be able to get there if they use current technology, because it costs so much more to move mass in space, and especially to the moon. It can be like $1 million for to move one water bottle. So by us saving them this mass, we can enable them to one, move faster, physically more velocity. We can allow them to go farther because it doesn't take as much propellant or fuel to move that mass. And then they'll have to have these tanks to support life on other planets, because you have a pressurized environment that has to contain air, and space is a vacuum. So it basically creates an optimal scenario. The tanks are are a key component. And one of the things that we met with Jim Bridenstine, the NASA administrator, last year, and he basically told me that cryogenic tanks are one of the key technologies that will help the U.S. maintain space supremacy, and it's one of the things that we don't currently have basically commercially available right now. And so I think that's a pretty powerful statement about tanks and why they're so important.
Super. Well, I wish we had more time, but we are out of time. And I've been joined by Matt Villarreal, who is the CEO of Infinite Composites Technologies. Thanks for joining today, Matt.
Yeah, thanks a lot, Scott.
If you've enjoyed this episode, take a moment to rate our show on any podcast platform that you listen to. Scroll down to the bottom and push 5 stars. It's that easy. And as always, thanks for listening.